Okay. Hello and welcome everyone to the last in series of the ASCE Spring Seminar. I've been told that my voice has been coming out really muffled in the past presentations, so I hope this $40 Amazon headphone really does a good job on it. Today, our last speaker, certainly not the least, is Dr. Halil Sezen. Dr. Sezen is a professor and faculty member of structural engineering at Ohio State University, where he's been teaching bridge engineering courses at OSU. He earned his Ph.D. at the University of California, Berkeley in 2002. He has authored more than 150 technical conference and journal publications. His research focuses on performance evaluation of buildings and other structures under extreme loading conditions. Dr. Halil, thank you very much. As always, if there are any questions, feel free to use the chat function and I will relay them to Dr. Sezen.
Thank you, Peyman. I attended a couple presentations over the last couple weeks or so, and the flavor of my presentation will be a little bit different, but hopefully it will benefit everyone. Today, we will talk about structural design. Although we are focusing on bridges, I will be comparing things with design of buildings and other structures all the time, because based on my background, I have been teaching and doing research on buildings and many different structures, including culverts. I do research on bridges, but over the last 2-3 years, I started to teach bridge engineering class at OSU. Then suddenly, I started to learn all the nitty-gritty details of ASCE and how things were different between analysis and design of buildings and other structures versus bridges. So based on that experience, I want to compare and contrast bridge design versus a design of other structures and codes and standards, and hopefully this will benefit everyone. Okay, good. So I just wanted to start with the structural design codes. In the US, if you are designing a building or any other structure like a tower or tank or whatever you can think of, you are required to follow a bunch of design codes and standards. So for example, for any structure, pretty much you have to calculate the loads, wind, live load, earthquake, ice, snow, whatever you can think of. Those loads must be calculated following the ASCE 7 standard. So all loads are calculated based on ASCE 7, including the load combinations needed for design, whether it is allowable stress design or LRFD. So ASCE is the standard. Pretty much all codes and standards adopt as the authority for load calculations and load combinations. Then if you're... Yes.
Sorry, we're not seeing this. Are you sharing the screen? Because we're not seeing anything.
Oh, yeah, something happened. This whole thing covered my... All right. Do you see it now?
Yes, we see the entire
okay.
slide.
For some reason, the chat screen on the side covered my entire screen. So please remind me if something goes wrong again. All right. So I was talking about ASCE 7. That's the standard that governs all load calculations. But then if your structure is a concrete structure, then you must follow ACI 318. Or if you have a steel structure, then you have to use AISC construction manual where you can follow either LRFD or ASD, but AISC is the governing code for steel material. And if you have a timber structure, then you have to follow NDS. A bunch of codes are governing the design of certain materials. And we also have this umbrella or model code called IBC, International Building Code. That makes things very convenient, because if you for counties and states and cities, if they want to deal with many different materials, it is very tough to adopt fire code and ACI and AISC differently. IBC pretty much combines all of them. So if the city of Columbus or county of, Franklin County or whatever, if they say we are adopting IBC, they automatically adopt ASCE 7, ACI, all these codes, and IBC adds a little bit of exceptions to there. Pretty much it is the same thing as other codes. There may be a little bit modifications here and there. So this is how the system works for buildings and other structures. Loads are coming from one standard, and each material has their own design code. The good news is when it comes to bridges, at the bottom of the slide, as you can see, as soon as you say I'm following AASHTO, a lot of these specifications, especially since 2010, if there is any government funding involved, you are required to follow AASHTO LRFD, then everything is self-contained. So in chapter 3 or 4, you learn about, or you calculate the loads, and then you go to chapter 6 and 10, and then if your structure is steel, you focus on one chapter, or if your material is concrete or decks, you focus on one chapter. So good news about AASHTO specifications is it is self-contained, everything is there, and then that's how you use it. So now in this presentation, I will be mostly focusing on ASCE 7 for load calculations, and I will just keep comparing AISC or IBC to AASHTO just to show the differences between the philosophies or thinking of these design codes. So if it will be a good idea to keep in mind what ASCE 7 is, what IBC, ACI means for building or other structural design to understand how things work. So if you are designing a structure out there, any structure, at this point in time, we have two different methodologies. The first one is the common one, and probably the second one will disappear over the next maybe 10, 20 years, maybe longer. The first one is called strength design or load and resistance factor design, LRFD. Concrete structures, whether precast structures governed by PCI or ACI, switch to LRFD or strength design completely in mid-1970s. So since then, all concrete structures are designed following the LRFD. There's no other way, there's no other option. Versus steel structures, even today, can be designed either by this LRFD or the ASD, which is the second methodology. You have the option as a designer to pick and choose. It is the same story with masonry and timber. Intentionally, I'm not talking about masonry and timber because they are less applicable for bridges. They are more or less like steel material as well. They are in the stages of shifting from ASD to LRFD. Older engineers tend to stick with ASD, and they like it because ASD is easier. But technically, from the theory point of view, ASD has some deficiencies. So future is LRFD and strength design. That's the right way to go, but it takes time to switch to that methodology. So just to put it out there, we have those two options. As I was saying a few seconds ago, all bridge structures starting with the 2010 edition of AASHTO had to shift to LRFD completely. At this point in time, bridge design follows LRFD procedure. Very briefly, what is allowable stress design? If you have a bridge structure, you need to check your stresses and deflections and many different things in addition to design of individual components. So all you do is you take the loads that are supposed to be applied on the structure during its lifetime, and you do structural analysis, and then you calculate the stresses in terms of stress checks, for example. The first term that you see here is the stress that you calculate from your structural analysis, and then you compare that with the allowable stress for that material. So if this is, for example, a steel structure, then AISC code says for the design of a beam, the allowable stress is equal to, let's say, 60% of the yield strength of the steel. If your calculated maximum stress is less than that limit, you are done. If not, you have to go back and change your design. Same thing for masonry or timber or whoever is following ASD. So the process is relatively straightforward and simple. That's the reason older engineers don't want to shift to LRFD. So this is how ASD works. You just use service loads, no load factors, no amplifications. And if you divide the allowable stress, which is capital F on the right-hand side, by the calculated stress, that also gives you a number that's called factor of safety. Okay, so if your allowable stress is, let's say 100 KSI, and if your calculated stress is 50 KSI, so that means your demand is 50% less. That means your factor of safety is equal to 2. When it comes to oh, I see, this drawing tool is giving me a hard time. Okay. Okay, so if I take the drawing tool, that's giving me a hard time. So when it comes to strength design, there is no such number as factor of safety. Just please remember that. So as we said, all concrete structures at this point in time must be designed by LRFD or strength design. And if somebody says, what is the factor of safety for this concrete beam, shear design or flexural design? The answer is, we don't know, because the factor of safety is embedded in the process. So what is the philosophy behind strength design? So if you look at the first bullet, I removed that red dot because for some reason it is giving me a hard time. So all we do is we calculate the demand on the left-hand side, and that comes from the factored loads. If you look at the bottom of the slide, MU is the maximum moment that comes from structural analysis, and then you have to multiply your loads separately by certain load factors. M sub D means it is the maximum moment coming from dead loads and is amplified by 20% by 1.2, and then your live load moments are amplified by 1.6. So those 1.2, 1.6 factors are your load factors that come from ASCE 7 or adopted by either AISC or ACI as a general process. So effectively, your MU or VU, which is the demand on your structure, whether it is a moment or shear or axial load, is amplified. So those load factors are typically larger than 1. That means your moment and shear demand is increased intentionally to provide some kind of factor of safety, but it is not explicit. So that's your demand. The demand is if you look at the second bullet point, it is the effect of applied external, maybe dead load applied on the structure. And it has nothing to do with the let's say material properties or the strength of the material, other than maybe a little bit dead load. So it is completely external load from the dead loads, wind loads, and all that stuff. Versus if you look at the right side of the inequality, now you are supposed to calculate the strength or resistance or capacity of the member or structure. And that capacity is also calculated at ultimate or failure or collapse. That's another difference between strength design and ASD or allowable strength design. LRFD design is done at the collapse level or failure or ultimate level. That's the reason we have M sub U. What it means is when we go through the LRFD design process, we are trying to prevent the collapse and failure of the structure. If there's a major earthquake or hurricane or unusual live load, as long as your structure doesn't collapse, you achieved your objective. that creates an issue actually with the owners of structures, because if you have a building leaning by 1 foot and all the beams and columns damaged completely and windows are gone and infill walls cracked and everything, if you ask the owner will say, oh, that's a terrible performance, now who's going to fix it? Versus if you ask the structural engineer, he or she will say, well, that's an acceptable, good performance, because under this major earthquake or hurricane, the building did not collapse because that was my target based on LRFD. So LRFD or strength design prevents the major failure or collapse of the structure. As long as you don't kill people and prevent the failure of the structure, you are achieving your objective. So that's the reason when we calculate the member strength or capacity on the right-hand side, we are calculating the maximum strength or maximum resistance. And if you look at the example at the very bottom, Mn or Vn are the nominal or actual maximum moment or shear strength of the member. And there is the last parameter in that example. The phi factor on the right-hand side is always less than or equal to 1. What it means is we are intentionally reducing our strength by a factor less than 1. So now if you look at the example at the bottom, when you look at MU and VU, they are increased, and then phi VN and phi MN are reduced. So we are comparing increased demand with the reduced capacity. And that gives us the safety and factor of safety and conservativeness in our process. But again, there is no single number that we can call factor of safety because it is embedded in that process. Okay, so I assume most of you guys already know this. I hope this will be a quick refresher. And now let's see how strength design or LRFD design is implemented. As I was saying about 5 minutes ago or so, ASCE 7 is the standard that governs all the loads and load combinations. And these are the 7 load combinations pretty much we have to follow. Let me see. D is the dead load, E is the earthquake, L is the live load. So these are the load combinations that you are supposed to use and analyze your structure ideally 7 times. And then whichever load combination gives you the largest moment axial load shear, you take that as your design force, and then make sure it will be less than the capacity, and that's how the design is done. Luckily, we have computers these days, and we can analyze the structure 7 times. In most cases, we know that 1 or 2 of these scenarios or combinations will govern our design after you keep doing the design. And again, very briefly, if you are designing a concrete structure, these are just a couple selected phi factors or strength reduction factors or resistance factors, depending on which code you are using. For flexural or bending design, if your member is controlled by tension, phi factor is 0.90, and then for shear design, it is 0.75. I intentionally pulled out those 2 numbers for a quick comparison in a few seconds. And if you are using ASCE for steel design or timber, we have similar factors. This is just an example for concrete structures. For flexure, it is 0.90, and then phi factor is 0.75 for shear design, just to do a quick comparison a little bit later. Okay, so now let's compare the process for bridge design versus all other structures. So just to remind ourselves, near the top of the slide, I repeated what I discussed so far. The LRFD process for buildings and other structures require that MU is less than or equal to phi MN, or VU is less than or equal to phi VN. That's the representation. In ASCE, though, it is exactly the same process, except for one little difference. That's the red pointed mu factor. That mu factor is called load modifier, and that includes 3 different factors. They are called ductility, redundancy, and importance. I put them in bold near the bottom of the slide. And as you can see, depending on whether your structure is brittle or non-ductile versus highly ductile, you may be able to reduce your demand or your loads 5% or increase them by 5%. So if we pick, for example, nu R, redundancy factor, so if your bridge doesn't have any extra members or highly non-redundant, then there's a penalty for you. You are required to increase your loads by 5%. Versus if you are using an indeterminate truss structure, for example, and if you are adding extra truss members, then you may be able to reduce your demands for those truss member design by 5%, and you use a nu factor of 0.95. So in an indirect way, ASCE is taking care of ductility, redundancy, and importance. So in ASCE 7 and also in the design codes, these factors are also considered. Ductility is very critical for seismic design, for example. It is explicitly considered also in ASCE. And then importance factor is also explicitly considered for ice, snow, rain, wind, and all of those. There are different importance factors. So ASCE is using a slightly different approach, regardless of the loads applied on the structure. It says you need to use these three load modifiers, and the rest of the process is exactly the same as other structures. Obviously, the load factors and phi factors are also different from ASCE 7, and we'll see them in a few seconds. There are a lot of unique differences between bridge structures and buildings and other structures. So this is one of them. It is the nature of the bridges, and all the soil loads and the varying surface and components are treated a little bit differently for bridge structures, and as it should be, it is the right way to do. Just to pick up the top two loads, DC and DW, and they are treated as a single dead load in ASCE 7. So if you were to design a bridge structure according to AISC or ACI, just for the sake of discussion, you cannot separate DC and DW. DC is the standard dead load for all the beams and columns and components. DW is the varying surface, asphalt-like material that you replace every 10 years, 15 years, whenever it is supposed to be replaced. So by definition, dead load is the permanent load, right? But as soon as you remove that varying surface, suddenly it looks a little bit live load. So ASCE takes care of that and then increase the load factor for varying surface. So that's the reason they have DW and DC separately. They are treated differently. Same with soil load. So if you are designing a steel or concrete structure, if it is not a bridge, then soil is pretty much treated like a regular dead load D. Same with live load. I just highlighted in orange color, whether you have vehicular load or pedestrian load, live load is live load in ASCE 7. Same with the wind load. So wind is wind and there's only one load, versus for bridge structures, they need to be a little bit treated differently because of the nature of the loads. A few slides earlier, I showed you summon load combinations from ASCE 7. Now, when we look at the ASCE, those summon load combinations in a little bit different way are repeated in that let's see, 7 rows highlighted by blue in the first column. They are all the way from strength 1 to strength 5, and then there are a couple extreme event 1 and extreme event 2 load combinations. All you do is, for example, if you are dealing with strength 2 load combination or limit state, you go to that row, and then in the second column you have all the permanent loads or dead loads, and then multiply them by the gamma P factor. I'll discuss that in a few seconds. And then you multiply for strength 2, you multiply your live loads by 1.35, and then you go to the rest of the table. If there's a load factor for certain load like temperature or other ones, you just multiply them, and that's your load combination. Like we said for ASCE 7, you have to repeat your analysis of the structure 7 times ideally, and then whichever load combination gives you the largest axial load, shear, or moment, that's your design demand. But in general, also for bridge structures, you don't need to do 7 analysis. Rather, you pretty much know which one governs the design. If you have high wind, for example, one of those strength limit states govern, or if you have earthquake, as I highlighted, extreme event 1 covers, and then most likely the other ones will not govern. Or if you have certain heavy live loads, one of them is going to govern. But theoretically, you are supposed to analyze your structure 7 times for all those blue load combinations. ASCE is also unique in a sense that it is good and bad. Load calculations are a little bit too crude and simple in ASCE in many scenarios. I just picked earthquake as an example. That's intentional. They don't even tell you, for example, what the load factor is going to be for live load if you have large earthquakes. So that's the reason I picked those 2 little orange highlights. So you calculate your earthquake load from chapter 4 of ASCE, and then when it comes to live load, pretty much you will have to follow what your specific state DOT says. So maybe that's the right way to go. If you are in California or West Coast, then Caltrans has all kinds of requirements that you have to follow. Even the calculation of the loads, whether it is the wind or earthquake, is much less detailed and simpler for bridge structures. I found out that that's probably intentional. That's what ASCE does, and but the process is pretty much the same, but the calculations are a little bit simple compared to other structures. So we'll talk about the dead load factor gamma p. That's a good news. Explicitly, the minimum and maximum load factors are discussed and handled in ASCE. Before I go to the next slide, maybe we can also talk about the bottom 6 load combinations. In the first column, I highlighted them in green. They are the service limit states. Effectively, they are picking up the ASD procedure in a way, in an indirect way, but we have the same thing for other structures. For example, if you are designing a pre-stress precast concrete member, you cannot tolerate concrete cracking in tension. So that's the reason you need to use those service limit states and calculate the stress, make sure it will be less than the stress limit. So for those, you need to use those service limit states. Okay, so this slide shows us the minimum and maximum load factors. So we have to do this on our own according to ASCE 7, but for bridge structures, it is explicit, and as a designer, you are supposed to pick the load combination that you need. This was challenging for our students. So I'll have a quick example in a few seconds. And again, for comparison purposes, if you are designing a bridge structure, if you look at this slide, for tension-controlled flexural members, your phi factor is 1. And for shear design, it is 0.9. I intentionally picked these 2 so that we can compare them with the building structures. If you remember, for buildings and other structures, phi factor was always 0.9. Now it is 1 for pre-stressed members. And also for shear design, it was 0.75. Now, according to ASCE, it is 0.90. So it is quite a bit different. So I wanted to do at least one simple comparison here. If you are designing a concrete garage structure using pre-stressed double T beams or something like that, precast beams. Then if you are checking that beam, prestressed beam for bending and shear, then you are supposed to use those two red and blue equations near the top of the slide. Okay, so according to ASCE 7, your load factors are 1.2, 1.6, and then your phi factor for flexure is 0.9, and then for shear it is 0.75. Same producer or manufacturer of the precast beam, let's say in Ohio, if those two beams are they may be exactly the same beams produced by a company in Mount Vernon, for example. They do it actually. They ship pre-stress or precast beams for a garage structure versus for a bridge. However, when you design those structures, if you look at the bottom load combinations, suddenly, let's say you are in a zone where wind is not huge or not a factoring or not a major factor in your design. I'd like to do one-to-one comparison. As you can see, just let's focus on bending. You have no reduction in your MN, and then your load factors are a little bit different. Maybe dead load is slightly larger and live load is slightly lower. And also when you look at the shear design, your reduction is much less for bridge structures. So precast industry bring this up all the time with ACI, but they can't break the resistance there because they complain that for bridges they do a better job, and there's more penalty for buildings. That's also for a reason, because bridge structures are inspected regularly, and if there's an issue, you can see in building structures, not typically, but mostly they are sometimes covered, and it's not easy to deal with them. So that's the reason. In general, this is not a 100% correct statement, but in general, buildings and other structures are a little bit conservative in this LRFD design process compared to bridge structures. The bridge structural design is a little bit less conservative even for other load and design scenarios. So I just wanted to put this out, but the good news is the process is identical. Assuming I handle the new factor in front of the bridge design, the process is very similar. If you look at the blue and red equations, they are pretty much the same thing if you can handle the numbers. So let's look at a quick scenario here. If I have a moment resisting frame as a structure, or this can be a bridge, and if it is pushed by wind on the left-hand side, how would I design the footing A for uplifting? So in order to have the uplift, I must definitely have a large wind force. So without the wind force, I cannot have the uplift. So that means the answer to this question should be either C or D. Now, the designer, the engineer has to decide whether live load must be included in the design or not. Okay, so live loads and dead loads are gravity loads. You cannot get rid of the dead load. That's the permanent weight or whatever that load may be. But the live load is up to the designer. So in this scenario, live load is acting against uplift. So that means it has to be out of the design equation. So that's the reason the answer to this problem must be C. You must be designing your footing A or the column on the left-hand side only for the dead load and your large wind load if you are suspecting uplift scenario for footing A. So now the question is, if this is a bridge structure or building structure, I put both of them, how would you numerically design your structure? You see, somebody has to literally go in there and pick these load combinations. The answer is, again, just to move quickly, has to be A in both scenarios. Now you can see that both ASCE 7 and ASCE became exactly the same load combination, same numbers. Why? Because we should be removing the live load. Suddenly the other options are gone. And also, if you pay attention, I told you earlier that for safer design to be conservative, we need to increase our dead loads, right? So if you look at the load factor in the correct option A, our dead loads are reduced by 10% to be on the conservative side. Why? Because if you reduce your dead load, your uplift force will be increasing, or your tension in that column will be increasing. That's what we want. We want the largest force. So again, here we are using the gamma minimum. If you are asking where did that 0.9 DC come from? See, ASCE has the minimum and maximum numbers. If you were to design the footing on the left-hand side, then your answer probably will be C for the bridge structure. You see, as an engineer, you decide on that 1.25 versus 0.9. Sometimes things get complicated, like in this example. Let me give you a few seconds. Why don't you think about this? If you were to be a bridge engineer and if you are designing this footing for just gravity loading, there's no lateral load, which load combination would you pick? Let me give you a few seconds to think about. Okay, so again, we are designing the footing A for uplift. And dead loads are permanent and we cannot get rid of them. So D1 must be there because it is pushing against that uplift. As we discussed in example number 1, D1 has to be reduced. So the answer has to be 0.9 times D1. So the answer D is immediately out. And when you look at the cantilever, you have the live load and you have the D3, and both of them are creating a tension on the right end of the structure. So if they are creating tension, if they are creating additional uplift, then their value must be increased. So if you go to a maximum and minimum gamma P factors, then D3 must be based on maximum gamma, which is 1.25. So in this example, the answer has to be C. So you are reducing your dead load 1, you are increasing your dead load 3, and you are also including and increasing your live load, which is 1.35 according to strength limit state 2. So if you look at answer C, that requires the judgment and interference and the knowledge of the engineer. So engineer has to decide that. If you just punch in the numbers and analyze your bridge structure, that will never happen. Computer doesn't know what the contribution of D1, D2, D3 is. Oh, by the way, D2 has no contribution or no effect on the response or design of column A. See, these are all the decisions of the engineer. So engineer has to really understand those gamma factors and think about all possible options. Okay, let's switch the gear and look at some other items. Progressive collapse has been actually becoming a major problem or design issue, and a lot of companies are doing a lot of work to prevent progressive collapse, especially if you are dealing with government buildings these days. It's almost required since especially 9/11 and over the last 10, 15, 20 years. So ASCE 7 defines progressive collapse as spread of damage after a local failure happens to the entire structure. So if your structure is designed well, your goal is to be able to contain that local initial failure and just keep it there and not lead the collapse of the entire structure. Okay, so in order to have a good design and not lead to entire structural collapse or disproportionately large collapse, you need redundancy. So the more members you have, the better your performance is. Ductility is another one. You can get a lot of deformations but not collapse. Continuity is another one. So those are the three major strategies that we do in buildings and other structures. If you lose a column in a building, if you can make the beam continuous right above that column, hopefully that beam is going to save the building and it's not going to collapse. By their nature, bridge structures are terrible against progressive collapse because of the redundancy. Bridge structures don't have too many redundant members because it's expensive, whether it is connections or the piers or truss members or beams. So if you lose a member, you tend to lose a large portion of the structure. So I just picked one. If you look at any bridge structure failure, I will call it progressive collapse based on the definition of ASCE 7. I just did a search a few days ago and picked up this Minnesota bridge collapse, but any bridge collapse pretty much, whether it is because of scar or whatever the reason, fits into progressive collapse definition. On the building side, this whole progressive collapse resistant design started in 1968 with that building collapse in London. There was an explosion in the upper floors, and then all these precast panels came down, and they started having all these requirements now. On the building side, we have a lot of requirements in individual codes, as well as we have different standards. So I just put a couple examples on the right-hand side for bridge progressive collapse. ASCE 7 specifically requires a check for progressive collapse, and this is extremely critical again for government structures because there's a requirement there. So there are three specific requirements in ASCE 7. They try to get away from the load itself. It can be because of impact, fire, blast, or even earthquake type things, but they call it extraordinary event AK. They say if you are, for example, designing a government structure, let's say in downtown Columbus, then you have to think about certain extraordinary event, let's say a truck hitting a column in the front of the building or something like that, and then you have to take care of the design using that AK load and then reanalyze your structure. This is on top of the 7 load combinations that we already discussed. And then also, if you look at the bullet at the bottom of the structure, you have to check your connections, anchorages, or continuity of the structure for a nominal load called N. Again, if you have to think about those extreme load scenarios like blast and fire, those kind of things, and then make sure your connections and beams, etc., will be able to resist them. And the middle one is relatively well established. So from the government documents, you are required to remove certain critical elements and then make sure the rest of the structure will be able to resist the loads defined in that load combination in the middle. So if I go to the next slide, for example, if you follow that ASCE load combination, then GSA and UFC are the government guidelines or codes. If you are designing, for example, a 20-story hotel structure or government structure in downtown Columbus, then you are required to remove 3 columns. If you look at the left-hand side, you are supposed to remove 1 corner column, 1 perimeter column from each side if they are not identical designs. And then when you remove 1 column, you have to demonstrate that your structure is not going to collapse. That's a requirement. So there are many requirements that I don't want to get into details, but and this is called alternate load path method. So you have to have, you should be able to redistribute loads through that alternate load path. And PCI or ACI or even AISC, they have their indirect design guidelines. For example, ACI 318 doesn't want to get into those specific loads. No one wants to deal with impact or blast or fire separately. Rather, they say we have these structural integrity guidelines where you have to tie things together, especially for precast structures, in the XY directions or also in the vertical direction. So if you lose a column or wall, rest of your structure should not collapse. So that's indirectly enforced, and that's what is done. Unfortunately, this is somewhat missing in bridge structures, but that's the nature of the structure. They are expensive, and you have to deal with them separately. So one major problem with bridge structures is the live load. For building structures, you may have many spans and your live load may change. So if you put your load in two adjacent spans, or one span loaded and the other one is skipped, that is acceptable according to for ACI 318 and AISC, and IBC is the umbrella code. That's what they specify. As long as you analyze your structure a few times for these load scenarios, you are done with live load variation or distribution. Versus this is a major problem with bridges, because your truck or unusual load can be anywhere on your bridge. So you are almost required to have some kind of influence light type analysis. I just wanted to put out here that any bridge that you are designing must be designed 2 times or analyzed 2 times. One for design truck shown on the screen, it's called HL93, and then one for the design tandem, which is 2 25 kip point loads moving on your bridge from one end of the bridge to the other end of the bridge. Plus, you have to have this uniformly distributed design lane load of 0.64 kips per foot length of the beam. So you have to put those 2 loads, whichever governs, and then design your structure accordingly following the guidelines. The challenge here is, where would you put your tandem or design track to design the bridge? So it may be easier for a simple, simply supported single span bridge, but if you have a multi-span bridge, that becomes an issue. For example, if you are designing the bridge deck for a simple, deck supported on girders, then you have 3 options. You can either do detailed finite element analysis. That's expensive. People don't want to do that, and they try to avoid as much as possible, because you also have a lot of options to put your loads. And then ASCE gives you a couple other options. You can use that equivalent strip method. That also is not so easy, but at least simpler than the first option. And then you have a very simple design option, number 3, I just want to show on the next page. As long as you meet certain criteria, ASCE gives you this table just as an example. If the distance or span between the girders is, let's say, 6.5 feet, then you go to this table and then you find out that your maximum positive moment between the 2 girders is 5 kips feet, and you just read it from that blue highlighted row in my table. I just wanted to put it out here. So ASCE is very good in providing some of these simplified approximations, but in many cases, because of the nature of the bridge structures, you are pretty much forced to do computer analysis, almost given, unless you have a very simple one span bridge structure. So as you can see on this slide, the stiffness and the flexibility of the girder and slab or deck makes a huge difference in your demand or capacity of your components. So if you look at the drawing at the top, it looks like okay, so it should, if it was a bridge, I would look at it, oh, okay, so it is a steel or concrete beams and concrete deck type thing. Versus here, it makes a huge difference if you have a timber beam versus steel beam versus concrete beam and the concrete deck, if you look at the three deflected shapes, depending on the relative rigidity of the beams and the deck, your results, your moments and shear and deflections and stresses will be very, very different. So I hope those three scenarios give you an indication of how they may look like. And the demand for the interior and exterior beams will be also very, very different. If your deck is too rigid versus too flexible, you will have very different scenarios. Okay, so again, in order to get around that, if you have this type of bridge, ASCE gives us some approximation so that we don't need to go through those 3D calculations. But if we don't meet the simplified rules, then we have to do computer analysis. So if your structure fits into some of these standard scenarios, then they give you, I just picked one green option in the middle. If you have one lane loaded in a scenario where all the lanes may be closed for an accident or repair or something like that, then you have to follow one equation. Or if you have multiple lanes loaded, they give you another option so that you can see the effect of live loads. And then if you look at the last row of this this table, there are a lot of requirements though. So if your bridge is a little bit skewed or unusual, or if there are other things going on, suddenly you are immediately forced into some kind of computer analysis. So I'll get that in a few seconds. Again, if you have multiple lanes loaded versus one lane loaded, and then depending on where your truck is, your results are very, very different. Live loads are very, very challenging. Again, if you can use, or if you are allowed to use, the simplified tables that I just showed you without getting into any numbers or anything like that, then you can use these type of simplified multiple presence factors, distribution factors, and then you can come up with the live load effect. So this is just one simple example. If you are designing, let's say, girder number 1 at the far left end, then you need to consider several scenarios. One scenario is to have that truck on the edge, truck number 1, and nothing else. And then you use those multiple presence factors and assume there may be other trucks. So things are very complicated. In some ways, if you are allowed, I will go with these simplified procedures, because doing these things using a computer is also very tough, because you have so many scenarios, so many possibilities, it becomes quite challenging. And then another challenge is how accurate your computer models are. So your other option is, if you don't want to use, or if you can't, or if you are not allowed to use them, to use influence lines. If you use a single 2D analysis, again, you have a lot of approximations. So in this simple example, this is supposed to represent influence line for a connection or connector on the left end of the structure. Then as you can see, for the rest of the structure, there's not much influence going on. But if your truck is moving right along that left edge, then you will have huge demands on that connector. So even developing these influence lines are tough. So I think I mentioned a few times by now, bridge structures are very challenging. That's the reason we have that value engineering you heard a few times over the last week or so. And then typically multiple independent engineers check the design as it should be. Because if I have a simple bridge like it's not that simple, but I will say relatively straightforward bridge, a prototype that is shown on the left-hand side, I have several options to design and represent that bridge. So I can go with the full finite element model, or I can go with grillage type model in the middle, or I can make a spine type model on the right-hand side. I can even turn this entire thing into a single 2D line. So I have all those options. But if my results are substantially different from someone else using the other options, then then there's an issue. So if you are, I intentionally picked the seismic analysis because for seismic design, in certain cases, it is perfectly fine and allowed to have a single degree system, which is a lollipop that is shown on the left end. That's the simplest representation versus just to design a connector or connection or a single element, you may need to do a finite element analysis, which is on the right end of the structure. And in certain cases, you may need to develop the finite element model for the entire structure. So the question is, which one is correct, which one is wrong? So in most cases, there is no correct or wrong answer. So I can take this bridge and ask two separate companies to design them using two finite element programs. And one company may come back and say stress at that critical location is 100 KSI, and then deflection is 5 inches. Another company may come and say stress is equal to 80 KSI, and then deflection is 1 inch. So it is not necessarily that one company or one model is wrong, the other one is correct. Rather, now they have to sit down and reconcile their modeling assumptions or analysis assumptions. So I believe both companies or both engineers have a right way of thinking in their modeling, but there are many options even for the same software. So that's the reason it is quite critical for bridge structures to have definitely multiple analysis, maybe not necessarily multiple finite element type analysis, but even those old engineers or experienced engineers may need to do some back of the envelope type things. Okay, so you are telling me 5-inch displacement or 3-inch displacement. Let me do a very quick check, maybe using a model that you see second on the left-hand side. So you can do simple hand calculations and see if the envelope or largest displacement should be, let's say, 5 inches or 3 inches or 1 inch. So bottom line is there should be multiple analysis, rightly so, and then there should be reconciliation, and then maybe a third independent check either from a DOT or from another company to make sure all the modeling assumptions and analysis assumptions are acceptable. So I just wanted to put a few concluding remarks here. If you are a good structural engineer, I've seen several of those, and if you have the opportunity to work for a company dealing with industrial structures or buildings, and if you are a bridge structural engineer, you can easily become or go to that company, and the process and analysis will be very similar. You already got the background knowledge. Or if you are working for building industry at this point or some other structural firm, and if you have the opportunity to move into bridge structural design, you can also easily handle things if you have the mechanics and analysis knowledge. So if you have PE, for example, I wouldn't see any major issues. Well, during the first 6 months or so, you will learn a lot of jargon and the basic things, and you will just keep learning. That's obvious. But at the end of the day, process is very similar. So it took a couple of years for me to learn certain things in bridge engineering design, but at the end of the day, it is the same process. So I've seen some engineers doing that. So if you feel like you are doing a good job in one company and switch to or from bridge engineering, that's not a scary thing to do if you know the process. And although there are unique differences, design of a bridge structure following LRFD or building is not too different. It is the same process. There are different factors and calculations and things like that. And then the live loads are the most challenging parts of the bridge design. That's normal. And then if you want to handle those, mainly live loads, then you are almost required to have influence lines or some detailed computer analysis. That's the reason actually in counties, let's say in Ohio or certain districts, they tend to use the same design and again. So if you go to a certain county, almost all of their single or simple single span bridges are concrete box bridges. When you talk to those engineers or the county engineers or companies, they say, oh, they feel very comfortable with design. Now I can see why, because whether the span length is 40 feet or 60 feet, they know that that design works, and they know that they have some maintenance and other issues, but they don't want to take the risk, and rightly so, because these live loads and other issues are creating so much problem. So once they find their niche and acceptable design, they just keep using it. Like box beam design, for example, is very common in Pennsylvania, Michigan, and Ohio. There are some maintenance and other issues, but they know it, but they still pick that design. And that's for a reason, because anytime you have a unique design, then you need to go through multiple analysis and multiple companies, multiple checks. You may still have some issues here and there. So that's the reason people feel much more comfortable using the same design. So I will just stop here. Oh, it is 12. It looks like I exceeded my time a little bit, but I'll be happy to take any questions if you have any questions. Thank you for your patience.
Thank you, Dr. Sezen. Let's see what we have. So, friends, if there are any questions, please use the chat function.
It looks like everything was so clear. I don't see any questions. I just turn on the chat room.
It appears to be no questions. So, if there are,
Okay, very good.
Email at the and I know I have your PDF of the presentation, so I will send that to the participants here shortly. Thank you very much, everyone, for attending.
Mm-hmm. Is there a question? I just saw something there. Is that a question or is it a general comment?
I think it seems to be a general comment here.
Oh, okay, good. One last thing I just remembered. I would strongly suggest our engineers in the region to take courses at OSU. Some of the companies are paying for the tuition. So the more you learn, the better it is for you guys. So even if you have a master's degree or PE, still I would suggest check the OSU website and take some advanced classes. It can be structural dynamics, earthquake engineering, or pre-stress concrete if you did not have to take, if you have not taken those type of courses. So I've had some students in the past, not only me, but we have several faculty members. That can be extremely helpful for you guys. You have that opportunity. I will encourage you guys to check the OSU courses and take them as a credit for you guys. Just a quick advertisement for the OSU.
Thank you. All right, thank you everyone for joining, and I will try to get all the PDFs hopefully out by tomorrow or early next week. All right, thank you very much everyone, and have a good day.
Thank you.
Thank you, Dr. Sezen.
Mm-hmm. Let me, how do I get out of